What's up everybody, Adele here. Today's video is a collection of all videos from our data manipulation and joining data with SQL courses. In these videos, you're going to learn about different types of joins, data aggregation and cleaning techniques in SQL, and a lot more. These are only just the videos, so if you want to practice what you learned, do check out the exercises that we've linked in the description below. And with that, happy learning.
Hello, my name is Maham Faisal Khan, and I'll be your instructor on a journey through the world of SQL joins. Joining data is an essential skill which enables us to draw information from separate tables together into a single, meaningful set of results. Although this course focuses on PostgreSQL, the material here applies to multiple forms of SQL. We'll begin with inner join, which along with left join makes up one of the two most common joins. Two tables, named left table and right table, are shown. Matching values of ID in both tables are shown in the same color. In both tables, the ID field is the key. A key is a single column or group of columns that uniquely identifies records in a table. Both tables also have fields called left val and right val, which will help visualize records returned after a join. With SQL joins, you can join on a key field or any other field. The inner join shown looks for records in both tables with the same values in the key field, ID. Arrows indicate records where the ID matches. In this diagram, we focus on records that match on ID and fade out any records that are not of interest to our inner join. The result is records with IDs 1 and 4. Throughout this course, we'll work with a database of world leaders. Our database schema is displayed here. It contains the presidents, prime ministers, and monarchs tables, as well as the states table containing independence years, and the prime minister terms table providing years the prime minister's assumed office. Let's start querying our database by selecting all fields from the presidents table. Recall the use of the asterisk in SQL to select all fields quickly. Here's a snippet of the prime minister's table from the same database. Suppose that we're interested in countries that have both a president and prime minister. In these small tables, we might notice that Egypt, Portugal, Pakistan, and India appear in both tables. For larger tables, though, it's not as feasible to identify these records by visual inspection. Here's where SQL joins can be helpful. The syntax for performing an inner join on our tables is shown step by step. It is common to begin constructing the query with the join first and selecting fields later. After from, we list the left table followed by the inner join keyword and the right table. We then specify the field to match the tables on using the on keyword. Here, we use the country field. Lastly, we add select at the start of the query and choose the fields we want returned. When selecting columns that exist in both tables, such as country and continent, the table.column_name format must be used to avoid a SQL error. The result of our query is displayed. 4 countries in our database have both presidents and prime ministers. In our inner join, we've had to type out president and prime minister several times. Luckily, we can alias table names using the same as keyword used to alias column names. Here, we use aliases P1 and P2 in both our select and on clauses to shorten our query. Before we end this lesson, let's add one more SQL shortcut to make our query even more concise. When joining on 2 identical column names, we can employ the using command, followed by the shared column name in parentheses. Here, since the join field is named country in both tables, we can use using. Now that we have written our very first SQL joins, it's time to think more conceptually about the kinds of relationships tables can have to each other. The first type of relationship we'll talk about is a one-to-many relationship. This is the most common type of relationship, one where a single entity can be associated with several entities. Think about a music library. One artist can produce many songs over their career. This is a one-to-many relationship. The same applies for authors and their books, directors and movie titles, and so on. Jane Austen wrote many books, and each of her books had just one author. In the table schema shown, each of her works are stored in the books table and can be merged with the authors table using author ID from both tables. A second type of relationship is a one-to-one relationship. One-to-one relationships imply unique pairings between entities and are therefore less common. A commonly held premise of forensic science is that no two fingerprints are identical, and therefore that a particular fingerprint can only be generated by one person. This is an example of a one-to-one relationship. One fingerprint for one finger. Imagine fingerprint scanning at airport border control. Border control might have two tables in a database, a table of people and a table of their prints. Each person's fingerprint could be merged with the individual's table using their passport number. We won't cover this in detail here, but using a binary format is one way to store images, such as fingerprints, in a database. Note here that although an individual will have 4 fingerprints stored in the fingerprints table, this is not a one-to-many relationship. It's a one-to-one relationship because a single individual, represented as one record on the individual's table, will have one set of fingerprints, represented as one record on the fingerprints table. The 4 different fingerprints are 4 different fields in each record. The last type of relationship we'll discuss is a many-to-many relationship. An example of this is languages and countries. Here we show the official languages of Germany, Belgium, and the Netherlands, where we see that many languages can be spoken in many countries. For example, Belgium has 3 official languages: French, German, and Dutch. Conversely, languages can be official in many countries. Dutch is an official language of both the Netherlands and Belgium, but not Germany. We've seen a few inner joins and thought about the relationships tables can have to each other. Now it's time to level up our joins by building on these ideas. A powerful feature of SQL is that multiple joins can be combined and run in a single query. Let's have a look at some syntax for multiple joins. We begin with the same inner join as before and then chain another inner join to the result of our first inner join. Notice that we use leftTable.id in the last line of this example. If we want to perform the second join using the ID field of right table rather than left table, we can replace leftTable.id with rightTable.id in the final line. Thinking back to our example of world leaders, let's say that we are interested in identifying countries of the world that have both a president and a prime minister and want to know the year each prime minister came into office. Let's have a look at the prime minister terms table from our database of world leaders. It contains a prime minister column with prime minister names as well as a PM start column containing the start year of a prime minister's term. Let's apply the new syntax we've learned to our world leaders example. We can begin as before with an inner join of the president's and prime minister's tables using our aliasing skills to shorten the length of the query. Recall from our first lesson that the result set of this join was a combined table showing countries with both a prime minister and a president. If we now join the result of our first inner join with our prime minister terms table on the prime minister field, the final result will be only those countries with both prime ministers and presidents, along with the years their prime ministers assumed office. Notice that the prime minister terms table has 10 records, whereas our final result only has 4 records. This is because only 4 records from the prime minister terms table match the result of our first inner join. Here's a look at the final SQL query for chaining a second inner join to our first inner join. Notice that the syntax for the second join is exactly the same as for the first join, but we use Prime Minister as the field to join on instead. We can continue the chain and join as many tables together as we need. Great work! Now, let's step back from our world leaders example. One more thing to know about joins is that it isn't always the case that each value in the field being joined on corresponds to exactly one record in the joining field of the right table. In the example shown, if we join on one field as we've done before, the query will return multiple records from right table that match with left table on the ID field. We can limit the records returned by supplying an additional field to join on by adding the AND keyword to our ON clause. In this example, we join on date, a frequently used second column when joining on multiple fields. The result set now contains records that match on both ID and date. Congratulations on completing Chapter 1 on inner joins, and welcome to Chapter 2 on outer joins, cross joins, and self joins. Recall the inner join diagram from Chapter 1. The only records in the result were those where the ID field had matching values in both tables. We'll now compare inner join with three types of outer joins, beginning with left join. Outer joins can obtain records from other tables even if matches are not found for the field being joined on. A left join will return all records in the left table and those records in the right table that match on the joining field provided. In the diagram shown, the values of 2 and 3 do not appear in the ID field of right table, but will still be retained in the join. Records that are not of interest to a left join on the ID field have been faded out. We now look at the result of the left join on ID. Inner join returns only records corresponding to IDs 1 and 4, whereas left join keeps all records in left table as well as null values for right val where there is no match in right table. Note that IDs 5 and 6 in right table do not feature in left join in any way. Let's go back to our world leaders example. Say we want our query to include all countries with prime ministers, presidents if they happen to have them, and missing values if they don't. Left join will give us the results we need. The syntax of left join is very similar to inner join. Only the word inner is replaced with left. Note that left join can also be written as left outer join in SQL. The first three records in the result are the same as they were with an inner join, but from the fourth record, the result starts to look different. Since the United Kingdom does not have a president, a corresponding null value is returned in the president field. On to right join. Right join is the second type of outer join and is much less common than left join, so we won't spend as much time on it here. Instead of matching entries in the ID column of the left table to the ID column of the right table, a right join does the reverse. All records are retained from right table, even when ID doesn't find a corresponding match in left table. Null values are returned for the left value field in records that do not find a match. Generic syntax for a right join is shown. Note that the order of left table and right table is the same as in left join. The only change is that we call right join instead of left join. Right join can also be written as right outer join in SQL. Let's make this concrete with our world leaders example. We perform a right join of prime ministers on the left and presidents on the right. The only change is from the left join keyword to right join. The result contains null values where countries have presidents, but no prime ministers. Now that you're familiar with both left and right join, let's discuss why right join is less commonly used. A key reason for this is that a right join can always be rewritten as left join. Because we typically type from left to right, Left join feels more intuitive to most users when constructing queries. Full join is the last of the three types of outer join. We'll compare full join to the two other types of join we've learned, left join and right join, as well as to inner join. A full join combines a left join and a right join. As you can see in this diagram, no values are faded out as they were in earlier diagrams. This is because the full join will return all IDs irrespective of whether they have a match in the other table being joined. Let's have a look at the result after full join. We see that it has retained all IDs, returning missing values in the form of nulls for fields corresponding to records where ID did not find a match. All 6 IDs we've been working with are included in the result after the full join. Note that this time, nulls can appear in either left value or right value fields. Time for some SQL code. In order to produce a full join, the general format aligns closely with the SQL syntax we've been using for inner join, left join, and right join. We adapt our join to have the word full before join. Note that the keyword full outer join can also be used to return the same result. Let's make our sample syntax concrete with our example from the leaders database. Suppose we were interested in all the countries in our database and wanted to check whether they had a president, a prime minister, or both. We'll walk through the code line by line to do this using a full join. The select statement starts us off by including the country as well as the prime minister and president fields. Next, we specify prime ministers as our left table and alias this as P1. Note that order of tables matters here, and if we switched the order, the records would be ordered differently depending on how prime ministers and presidents are ordered in the tables. We then add the full join query and add presidents as the right table using alias P2. Lastly, the join is performed using country as the field to join on in both tables. We limit to the first 10 records. Here's a look at our result. Note that there are null values in both the prime minister and president fields. We chose a full join because we were interested in all countries, whether they had a prime minister, a president, or both. Now that we've worked with inner joins and 3 types of outer joins, we'll be checking out cross join. Cross joins are slightly different than joins we've seen previously. They create all possible combinations of 2 tables. Let's explore the diagram for a cross join. In this diagram, we have 2 tables named Table 1 and Table 2 with 1 field each, ID 1 and ID 2 respectively. The result of the cross join is all 9 combinations of the ID values of 1, 2, and 3 in Table 1 with the ID values of A, B, and C for Table 2. Let's have a look at the syntax for cross join. Note that the syntax is very minimal and that we do not specify on or using with cross join. Let's apply the SQL syntax for a cross join to the following problem that uses our database of global leaders. Suppose that all prime ministers in Asia from our database are scheduled for individual meetings with all presidents in South America from our database, and we're journalists who wish to follow all the meetings that will happen. We can create a query that returns all these combinations using a cross join. We use a where clause to focus only on prime ministers from Asia and presidents from South America. The results of the query give us all possible pairings of the 4 prime ministers from Asia in the prime ministers table and the 2 presidents from South America in the presidents table. Well done getting to the last lesson of this chapter. We'll now dive into a special kind of join, where a table is joined with itself. These types of joins are called self-joins. Joining a table to itself may seem like an unusual thing to do. Why would we want to do that? Self-joins are used to compare values from part of a table to other values from within the same table. Recall the Prime Minister's table from earlier. Suppose all prime ministers are convening in summits on their own continents. We want to create a new table showing all countries in the same continent as pairs. Self-joins don't have dedicated syntax as other joins we've seen do. We can't just write self-join in SQL code, for example. In addition, aliasing is required for a self-join. Let's look at a chunk of inner join code using the Prime Minister's table. The country column is selected twice, and so is the continent column. The Prime Minister's table is on both the left and the right of the join, making this both a self-join and an inner join. The vital step here is setting the joining fields which we use to match the table to itself. For each country, we will find multiple matched countries in the right table since we are joining on continent. Each of these matched countries will be returned as pairs. Since this query will return several records, we use limit to return only the first 10 records. The results are a pairing of each country with every other country in the same continent. However, note that our join also paired countries with themselves, since they too are in the same continent as themselves. We don't want to include these since a leader from Portugal does not need to meet with themselves, for example. Let's fix this. Recall the use of the AND clause to ensure multiple conditions are met in the ON clause. In our second condition, we use the not equal to operator to exclude records where the p1.country and p2.country fields are identical. Here's a look at our final table, showing combinations of countries in our database that are in the same continent, but excluding records where the two country fields are the same. Welcome back for Chapter 3. In this chapter, we explore a new way of joining data, set operations. Along the way, we'll highlight key differences between set operations and the joins we've seen so far. SQL has three main set operations: union, intersect, and except. The Venn diagrams shown visualize the differences between them. We can think of each circle as representing a table. The green parts represent what is included after the set operation is performed on each pair of tables. In this lesson, we'll cover union and union all. Let's take a closer look at how they work. In SQL, the union operator takes two tables as input and returns all records from both tables. The diagram shows two tables, left and right, and performing a union returns all records in each table. If two records are identical, union only returns them once. To illustrate this, the first two records of the right table have been faded out. Our result has 7 records. In SQL, there is a further operator for unions called union all. In contrast to union, given the same two tables, union all will include duplicate records. Therefore, performing union all on this data will return 9 records, whereas union only returned 7. No records have been faded out. The syntax for performing all the set operations in this chapter is highly similar. We perform a select statement on our first table, a select statement on our second table, and specify a set operation, in this example either union or union all, between them. Note that set operations do not require a field to join on. This is because they do not do quite the same thing as join operations we covered in earlier courses. Rather than comparing and merging on the left and right, they stack fields on top of one another. For all set operations, the number of selected columns and their respective data types must be identical. For instance, we can't stack a number field on top of a character field. The result will only use field names, or aliases if used, of the first select statement in the query. We now return to our world leaders example. In this example, we use one more table from our leaders database, the monarchs table. Of course, this table is only a sample of monarchs and not a comprehensive list of monarchs across the world. We can use union on the monarchs and prime ministers tables to show all the different prime ministers and monarchs in these two tables. Note that the monarch field has been aliased as leader. As we've learned, the monarch and prime minister fields will be combined under the leader field, even though we only aliased the monarch field. We'll limit to the first 10 results so they fit on our screen. Our union returns the top 10 monarchs, prime ministers, and their corresponding countries. Does something stand out here? Recall that the monarchs for Oman and Brunei are also prime ministers. Union only lists them once each because they are the same person. Norway is listed twice, however, because its monarch and prime minister are different people. This is where a union all is helpful. A union all will tell us if there are any monarchs who also act as prime ministers. The syntax for this is shown. After union all, Brunei and Oman are now listed twice. In this lesson, we'll explore our next set operation, intersect. Intersect takes two tables as input and returns only the records that exist in both tables. In the diagram shown, we have two tables, left table and right table. The result of performing intersect on these tables is only the records common to both tables, the first record. All records that are not of interest to the intersect operation are faded out. The syntax for this set operation is very similar to that of union and union all. We perform a select statement on our first table, a select statement on our second table, and specify our set operator between them. Let's compare intersect to performing an inner join on two fields with identical field names. Similar to union, for a record to be returned, intersect requires all fields to match, since in set operations we do not specify any fields to match on. This is also why it requires the left and right table to have the same number of columns in order to compare records. In the figure shown, only records where both columns match are returned. In inner join, similar to intersect, only results where both fields match are returned. Inner join will return duplicate values, whereas intersect will only return common records once. As we know from earlier lessons, inner join will add more columns to the result set. Let's have a look at how we can use intersect to determine all countries that have both a prime minister and a president. Each select statement in our query has the same number of columns of identical data types in order for the set operation to be performed. The result of the query is the 4 countries with both a prime minister and a president in our leaders database. As with union, the result set uses the field names provided for the left table, whether aliased or not. Next, let's think about what would happen if we selected 2 columns, country and prime minister, instead of just country, as in our previous example. The code shown does just that. What will the result of this query be? Will this also give us the names of countries that have both a prime minister and a president? The actual result is an empty table. Why is that? As we saw in our intersect diagrams, intersect requires data from both fields in the left table to match their corresponding fields in the right table. The search did not find any countries where the prime minister and president share the same name. However, recall that there are monarchs in our database who also act as prime ministers. In the example shown, performing an intersect on the prime ministers and monarchs tables using both country and leader name does not return an empty result. We are now at the last of our set operations in this course. Except allows us to identify the records that are present in one table but not the other. More specifically, it retains only records from the left table that are not present in the right table. The diagram shown illustrates the workings of the except operation. All records that are not of interest to the except operation are faded out. Only the last 2 records of the left table are returned. Note that while the ID 4 does exist in the right table, the whole record does not match, which is why the last record of left table is not faded out. We saw earlier that there are some monarchs that also act as the prime minister for their country. Let's say we were interested in monarchs that do not also hold the title of prime minister. The except clause is really handy for this. The SQL code shown selects the monarch and country field from monarchs and then looks for common entries in the prime minister and country fields in the prime minister's table, looking to exclude those entries. In the result, we see only the 3 monarchs from our leaders database who do not also serve the role of prime minister. We've made it to the final chapter of this course. Keep up the excellent work. In this lesson, we'll return to joins one last time with an introduction to nested SQL queries. The 6 joins we've worked with so far are all additive in that they add columns to the original left table. The diagram shows an inner join on the ID field, showing an additional column being added to the original left table. Here is some familiar inner join syntax for this join on the ID field. Let's dive deeper into what it means for this join to be additive. Fields with different names are added to the results set with their original names. Fields with the same name, such as date, are added to the results set too, but notice how we now have duplicate date columns with the same name. This can be changed, however, with aliasing. In this lesson, we'll see ways of joining data that do not expressly use join keywords and are not additive in the same way. Instead of using join or set operators, we can leverage the where clause to specify the records to include. We'll use the 2 tables, left table and right table, in the diagram shown. A semi-join chooses records in the first table where a condition is met in the second table. More specifically, the semi-join will return all values of left table where values of call 1 are in a column we specify, namely call 2 in the right table. Records not of interest to the semi-join have been faded out. The final result of our semi-join is records corresponding to IDs 2 and 3. Let's make this concrete with an example. Suppose we're interested in determining the presidents of countries that gained independence before 1800. We select the fields country, continent, and president. How do we filter this data for independence year, which is a field in the states table? We'll use a semi-join. Before we knew anything about joins, we knew we could leverage the where clause to filter data. The query that returns countries with independence year before 1800 is shown. The query returns only Spain and Portugal from our database. We can use this list of countries as a filter by embedding it in a further where clause. This is called a subquery. It chooses records in the first table where the country matches the list returned by our subquery. Since Spain does not have a president, only the Portuguese president is listed. Moving on to anti-joins. The anti-join chooses records in the first table where column 1 does not find a match in column 2. The final result of our anti-join is records corresponding to IDs 1 and 4. Again, no new columns are added. How might we adapt our semi-join to determine countries in the Americas founded after 1800? To change our semi-join from before to after 1800, we add not before the in statement. We call this an anti-join. In addition, we add to our first where clause to filter for continents in the Americas. The result shows presidents of countries in the Americas that gained independence after 1800. Only Chile and Uruguay are returned, not the USA, which gained independence before 1800. Note again that we are only using the few countries in our database for illustration. This is not a comprehensive list of countries in the world. In this lesson, we'll dive deeper into embedding queries within queries. We'll revisit subqueries within a where clause and then go on to subqueries within a select statement. The semi-joins and anti-joins we've seen so far involve subqueries inside where. The where clause is the most common place for subqueries because filtering data is one of the most common data manipulation tasks. Let's revisit this with some generic syntax and understand the nuances of this type of subquery. Have a look at the query shown. Recall that the where-in clause enables us to provide a list of values to filter on. As we've seen in the lesson on semi-joins, arguments to the in operator are not limited to lists typed out by us. We can include a SQL subquery as an argument for the in operator, provided the result of the subquery is of the same data type as the field we're filtering on. The query shown will only work if sum underscore field is of the same data type as sum underscore numeric underscore field, because the result of the subquery will be a numeric field. Subqueries inside where can be from the same table or from a different table, and here the subquery is from a different table. The second most common type of subquery is inside a select clause. Say we want to count the number of monarchs listed in the monarchs table for each continent in the states table. Again, let's build up our solution step by step. The query shown selects each of the 5 continents in the states table, and the result is displayed. In earlier courses, we've seen the use of group by to count data by a group. However, since our monarchs data lives in a different table than the states table, this would involve a careful join before the group by. Let's look at how to do this with a subquery instead. Our subquery requires 2 things. First, it needs to count all monarchs. Second, it needs a where statement matching the continent fields in the 2 tables. This subquery follows the selection of distinct continents and will therefore count all monarchs within them in the select statement. A subquery inside a select statement like this requires an alias, like monarch underscore count here. Magic. The last type of subquery we'll cover is a query inside a from clause. Let's dig in. Let's say we're interested in all the continents with monarchs, along with the most recent country to gain independence in that continent. A starting SQL query to pull all the most recent independence years by continent is shown. The query groups records by continent and returns the most recent independence year for each group by using the max function as most underscore recent. The result set is shown. Now, how do we filter this for continents with monarchs? We haven't seen yet that we can include multiple tables in a from clause by adding a comma between them. In the SQL syntax shown, we include 2 different tables, left table and right table, in our from clause. The diagram shown illustrates that this query returns duplicates for multiple occurrences of ID when it matches in both tables. We can drop duplicates using the distinct command in the query shown. Let's investigate a way to solve our problem using this trick. We can nest the subquery we initially wrote into a from statement so that we are selecting from both monarchs and our subquery, aliased as sub. We also use the where clause as before to identify records in both tables that match on continent. As we saw on the previous slide, because the continents from our subquery will find multiple matches in monarchs, this match will return duplicates. As before, in our select statement, we use the distinct command to drop duplicate continents and select sub.mostRecent to get the most recent independence year for each continent. Lastly, we order by continent. Have a look at our result set. There we have it, the continents with monarchs in our database, and the most recent year of independence in those continents. That's how we include a subquery as a temporary table in our from clause and then select from it. Let's do a rapid roundup of everything we've learned. We talked a lot about joins. In SQL, a join combines columns from one or more tables in a relational database via a lookup process. We learned about inner join, left join, right join, full join, and cross join. We also learned about semi-joins, anti-joins, and self-joins. We also covered a different way of joining data in SQL, set operations. Lastly, we covered subquerying, which is covered in more detail in later SQL courses by DataCamp. We saw subquerying inside the select, where, and from clauses. If you'd like to continue on your journey to becoming a SQL pro, we recommend you take the SQL course listed. If you'd like to continue practicing joining data, have a look at some projects, practice exercises, and competitions. Alternatively, head to Workspace to build a portfolio of your own projects. Good luck on your future endeavors.
Hello, and welcome to Intermediate SQL. My name is Mona Khalil. I am a curriculum lead with DataCamp, and I will be your instructor for this course. SQL is a powerful tool for working with relational databases. With an intermediate knowledge of SQL, you will gain the ability to access and create robust datasets from multiple tables in a relational database to answer your data science questions. In this course, you will specifically learn how to shape, transform, and manipulate data using the case statement, simple subqueries, correlated subqueries, and window functions. Before taking this course, you should be comfortable working with introductory SQL topics such as selecting data from a database using arithmetic functions, group by statements, and where clauses to filter data. In short, the query on the top should look pretty familiar to you. You should also be familiar with joining data with a left join, right join, inner join, and outer join. In this course, we will use and build upon these topics to interact with our database. All right, let's get started. For this course, we will be using the European Soccer Database, a relational database that contains data about over 25,000 matches, 300 teams, and 10,000 players in Europe between 2008 and 2016. The data is contained within 4 tables: country, league, team, and match. Selecting from tables in this database is pretty simple. The query you see here gives you the number of matches played in each of the 11 leagues listed in the league table. Let's say we want to compare the number of home team wins, away team wins, and ties in the 2013-2014 season. The match table has 2 relevant columns: home goal and away goal. We can potentially add filters to the where clause, selecting wins, loses, and ties as separate queries, but that's not very efficient if you want to compare these separate outcomes in a single data set. This is where the case statement comes in. Case statements are SQL's version of an if this, then that statement. Case statements have 3 parts: a when clause, a then clause, and an else clause. The first part, the when clause, tests a given condition, say x equals 1. If this condition is true, it returns the item you specify after your then clause. You can create multiple conditions by listing when and then statements within the same case statement. The case statement is then ended with an else clause that returns a specified value if all your when statements are not true. When you have completed your statement, be sure to include the term end and give it an alias. The completed case statement will evaluate to 1 column in your SQL query. In this example, we use a case statement to create a new variable that identifies matches as home team wins, away team wins, or ties. A new column is created with the appropriate text for each match given the outcome. In the next lesson, we will practice more ways of structuring case statements using arithmetic functions such as count, sum, and average. Previously, we covered case statements with one logical test in a when statement, returning outcomes based on whether that test is true or false. This example tests whether home or away goals were higher and identifies them as wins for the team that had a higher score. Everything else is categorized as a tie. The resulting table has one column, identifying matches, as one of three possible outcomes. If you want to test multiple logical conditions in a case statement, you can use AND inside your when clause. For example, let's see if each match was played and won by the team Chelsea. Let's see the case statement in this query. Each when clause contains two logical tests. The first tests if a home team ID identifies Chelsea, and then it tests if the home team scored higher than the away team. If both conditions are true, the new column output returns the phrase Chelsea home win. The opposite set of conditions are included in a second when statement. If the away team ID belongs to Chelsea and scored higher, then the output returns Chelsea away win. All other matches are categorized as a loss or a tie. Here's the resulting table. When testing logical conditions, it's important to carefully consider which rows of your data are part of your else clause and if they're categorized correctly. Here's the same case statement from the previous slide, but the where filter has been removed. Without this filter, your else clause will categorize all matches played by anyone who don't meet these first two conditions as loss or tie. Here are the results of this query. A quick look at it shows that the first few matches are all categorized as loss or tie, but neither the home team ID or away team ID belong to Chelsea. The easiest way to correct for this is to ensure you add specific filters in the where clause that exclude all teams where Chelsea did not play. Here, we specify this by using an OR statement in where, which retrieves only the results where ID 8455 is present in the home team ID or away team ID columns. The resulting table from earlier, with the team IDs in bold here, clearly specifies whether Chelsea was home or away team. It's also important to consider what your else clause is doing. These two queries here are identical, except for the else null statement specified in the second. They both return identical results, a table with quite a few null results. But what if you want to exclude them? Let's say we're only interested in viewing the results of games where Chelsea won, and we don't care if they lose or tie. Just like in the previous example, simply removing the else clause will still retrieve those results and a lot of null values. To correct for this, you can treat the entire case statement as a column to filter by in your where clause, just like any other column. In order to filter a query by a case statement, you include the entire case statement, except its alias, in where. You then specify what you want to include or exclude. For this query, I want to keep all rows where the case statement is not null. my resulting table now only includes Chelsea's home and away wins, and I don't need to filter by their team ID anymore. Let's take a look at case statements with aggregate functions. Case statements can be used to create columns for categorizing data and to filter data in your where clause. You can also use case statements to aggregate data based on the results of a logical test. Let's say you wanted to prepare a summary table, counting the number of home and away games that Liverpool won in each season. If you've created summary tables in spreadsheets, you can probably visualize the final table here. But how do you get a count of Liverpool's wins in each season? You guessed it, a case statement. Case statements are like any other column in your query, so you can include them inside an aggregate function. Take a look at the case statement. The when clause includes a similar logical test to the previous lesson. Did Liverpool play as the home team? And did the home team score higher than the away team? The difference begins in your then clause. Instead of returning a string of text, you return the column identifying the unique match ID. When this case statement is inside the count function, it counts every ID returned by this case statement. You then add a second case statement for the away team and group the query by the season. When counting information in a case statement, you can return anything you'd like. A number, a string of text, or any column in the table. SQL is counting the number of rows returned by the case statement. Similarly, you can use the sum function to calculate a total of any value. Let's say we're interested in the number of home and away goals that Liverpool scored in each season. This is fairly simple to set up. If the home team ID is Liverpool's, return the home goal value. The else clause is assumed to be null. So the query returns the total home goals scored by Liverpool in each season. You can also use the average function with case in two key ways. First, you can calculate an average of data. You can do this using the case in the exact same way you just used the sum function. Just change out the sum for average in this query, and instead you get the average goals Liverpool scored in each season. You can make the results easier to read by using round. Round takes two arguments, a numerical value and the number of decimal points to round the value to. Place it outside your aggregate case statement and include the number of decimal points at the end. There, that's much easier to read. The second key application of case with average is in the calculation of percentages. This requires a specific structure in order for your calculation to be accurate. The question we're answering here is, what percentage of Liverpool's games did they win in each season? The first component of this case statement is a when clause, identifying what you're calculating a percentage of. In this case, how many games did they win? This is tested in the same way as the previous slides, and your then clause returns a 1. The second component identifies Liverpool's games that they lost and returns a value 0. All other matches, ties, games not involving Liverpool, are excluded as nulls. Here are the results of this query. And here's the rounded, more readable version of the results. In this chapter, we will cover the use of simple subqueries to extract and transform your data. A subquery is a query nested inside another query. You can tell that there is a subquery in your SQL statement if you have an additional select statement contained inside parentheses surrounded by another complete SQL statement. So why is this important? Often, in order to retrieve information you want, you have to perform some intermediary transformations to your data before selecting, filtering, or calculating information. Subqueries are a common way of performing this transformation. A subquery can be placed in any part of your query, such as the select, from, where, or group by clause. Where you place it depends on what you want your final data to look like. A subquery can return a variety of information, such as scalar quantities or numbers, like the ones listed here. A subquery can return a list to use for filtering or joining information, or it can return a table to extract and further transform data. So why might you need to use a subquery? Subqueries allow you to compare summarized values to detailed data. For example, compare Liverpool's performance to the entire English Premier League. Subqueries also allow you to better structure or reshape your data for multiple purposes, such as determining the highest monthly average of goals scored in the Bundesliga. Finally, subqueries allow you to combine data from tables where you're unable to perform a join, such as getting both the home and away team names into your results table. We'll discuss all of these questions in the coming lessons. Let's start with the definition of a simple subquery. A simple subquery is a query nested inside another query that can be run on its own. The example you see here has a subquery in the where clause. If you copy the entire inner query, select average home goal from the match table, you can run it on its own and get a result. A simple subquery is also evaluated once in the entire query. This means that SQL first processes the information inside the subquery, gets the information it needs, and then moves on to processing information in the outer query. Here's the same query you see above. The subquery in where is processed first, generating the overall average of home goals scored. SQL then moves on to the main query, treating the subquery like the single aggregate value it just generated. The first type of simple subquery we'll explore is the subquery in the where clause. These are useful for filtering results based on information you'd have to calculate separately beforehand. Let's generate a list of matches in the 2012-2013 season where the number of home goals scored was higher than the overall average. You could calculate the average and then include that number in the main query, or you could put the query directly into the where clause inside parentheses. This way, you have one less manual step to perform before getting the results you need. Subqueries are also useful for generating a filtering list. This query answers the question, which teams are part of Poland's league? The team table doesn't have the country IDs, but the match table has both country and team IDs. By querying a list of home team IDs from match, where the country ID is 15722, which indicates Poland, you can generate a list to compare the team API ID column in the where clause. In this lesson, we will cover the use of subqueries in your from statement. You probably noticed that subqueries in where can only return a single column. But what if you want to return a more complex set of results? subqueries in the from statement are a robust tool for restructuring and transforming your data. Often, the data you need to answer a question is not yet in the format necessary to query it directly and requires some additional processing to prepare for analysis. For example, you may want to transform your data into a different shape or pre-filter it before making calculations. Subqueries in a from statement are a common way of preparing that data. Subqueries in from are also useful when calculating aggregates of aggregate information. Let's say you're interested in getting the top 3 teams who scored the highest number of home goals on average in the 2011-2012 season. You would first calculate the average for each team in the league, and then calculate the max value for any team overall. This can be easily accomplished with a subquery in from. Let's examine the home goal average for every team in the database. First, you will create the query that will become your subquery. This query here selects the team's long name from the team table and the average of home goal column from the match table. The team table is left joined onto the match table using home team ID, which will give you the identity of the home team. The query is then filtered by season and grouped by team. The results look like this: an average value calculated for each team in the table. In order to get only the top teams as a final result, place this entire query without the semicolon inside the from statement of an outer query. Make sure to give it an alias, then add it to the main query, selecting the team and home average columns from the subquery, just as you would with any other table in the database. Finally, don't forget to order by home average descending and limit the query to 3 results. The final query returns your top 3 teams based on home goals scored in the 2011-2012 season. And it seems that our top team for that season is Barcelona. There are a few key things to remember when using subqueries in the from statement. The first is that you have the ability to create more than one subquery in the from statement of any main query. When you do so, make sure you give each subquery an alias and make sure that you are able to join them to each other, just as you would when querying a table from your database. Second, you can join a subquery to any existing table in your database. Again, however, you need to make sure you have a column in the subquery that you can use with the join you'd like to perform. We've covered the use of simple subqueries in from and where statements. Subqueries can also be included in a select statement to bring summary values into a detailed dataset. Subqueries in select are used to return a single aggregate value. This can be fairly useful since, as you'll recall, you cannot include an aggregate value in an ungrouped SQL query. Subqueries in select are one way to get around that. Subqueries in select are also useful when performing complex mathematical calculations on information in your dataset. For example, you may want to see how much an individual score deviates from the average, say, how much higher than the average is this individual score. Including a subquery in select is fairly simple and is set up the same way you set up subqueries in the where and from clauses. Let's say we want to create a column to compare the total number of matches played in each season to the total number of matches played overall. We can first calculate the overall count of matches across all seasons, which is 12,837. We can then add that single number to the select statement, which yields the following results, or we can skip that step and add the subquery directly to the select statement to get identical results. Subqueries and select are also incredibly useful for calculations with the data you are querying. The single value returned by a subquery in select can be used to calculate information based on existing information in a database. For example, the overall average number of goals scored in a match across all seasons is 2.72. If you want to calculate the difference from the average in any given match, you can either calculate this number ahead of time in a separate query and input the value into the select statement, or you can use a subquery that calculates this value for you in your select statement and subtract it from the total goals in that match. Overall, this second option can save you a lot of time and errors in your work, and the results you see here are identical to calculating the result manually. There are a few unique considerations when working with subqueries in Select. The first is that the subquery needs to return a single value. If your subquery returns multiple rows, your entire query will generate an error. This is because the information retrieved in a select query is applied identically to each row in the dataset, and that's not possible if there's more than one unit of information. The second thing to keep an eye out is the correct placement of your data's filters in both the main and the subquery. Here's the query from the previous slide. Since the subquery is processed before the main query, you'll need to include the relevant filters in the subquery as well as the main query. Without the where clause you see here, in the subquery, the number returned would have been the overall average across all seasons, rather than in the 2011-2012 season. Let's look at the use of multiple subqueries in one query and some best practices for making sure your queries are as readable as possible. In SQL, you can include as many simple subqueries as you need within multiple clauses within your query. However, your queries can quickly become long and difficult to read. For example, the query you see here includes a subquery in the select, from, and where statements. You don't have to read through this now, but it's worth getting a sense of how extensive SQL queries can get and discuss some best practices for reading and writing large queries. The best practice you can start early on in your SQL journey is properly formatting your queries. It's important to properly line up your select, from, group by, and where statements, and all of the information contained in them. This way, you and others who you work with can return to a saved query and easily tell if these statements are part of a main query or a subquery. It's also considered best practice to annotate your queries with comments in order to tell the user what it does, using either a multiple line comment inside a /* and ending with a star and a /. You can also use inline comments using 2 dashes. Every piece of information after an inline comment is treated as text, even if it's a recognized SQL command. Additionally, make sure that you properly indent all information contained within a subquery. That way, you can easily return to the query and understand what information is being processed first, where you need to apply changes, such as to a range of dates, and what you can expect from your results if you make those changes. Make sure you clearly indent all information that's part of a single column, such as a long case statement or a complicated subquery in Select. In order to best keep track of all the conditions necessary to set up each when clause, each then clause, and how they create the column outcome, it's important to clearly indent each piece of information in the statement. Overall, I highly recommend you read Hollywell's SQL Style Guide to get a sense of all the formatting conventions when working with SQL queries. When deciding whether or not you need a subquery, it's important to know that each subquery you add requires additional computing power to generate your results. Depending on the size of your database and the number of records you extract in your query, you may significantly increase the amount of time it takes to run your query. So it's always worth asking whether or not a specific subquery is necessary to get the results you need. Finally, when constructing a main query with multiple subqueries, make sure that your filters are properly placed in every subquery and the main query in order to generate accurate results. The query here, for example, filters for the 2013-2014 season in 3 places. Once in the Select subquery, once in the Where subquery, and once in the main query. This ensures that all data returned is only about matches from the 2013-2014 season. Now that you've covered the basics of simple subqueries, let's learn how to construct correlated subqueries. Correlated subqueries are a special kind of subquery that use values from the outer query in order to generate the final results. The subquery is re-executed each time a new row in the final data set is returned in order to properly generate each new piece of information. Correlated subqueries are used for special types of calculations such as advanced joining, filtering, and evaluating of data in the database. Let's walk through an example of one of these queries. In the previous chapter, you completed an exercise that answered the question, which match stages, where the stakes get higher in each stage, tend to have a higher than average number of goals scored. You achieved this using 3 simple subqueries in the Select, From, and Where statements. However, that same output can also be produced with a correlated subquery. Let's focus on the subquery in the Where statement. This query only has one difference. Instead of including a filter by season, the Where clause filters for data where the outer table's match stage, pulled from the subquery in From, is higher than the overall average generated in the Where subquery. The entire Where statement is saying, in essence, return stages where the values in the subquery are higher than the average. Here are the results generated by this query. This may seem a bit complicated, but with a few more examples and a bit of practice, you will start to get the hang of how useful correlated subqueries can be. Let's quickly walk through some key differences between simple and correlated subqueries. Simple subqueries can be used in extracting, structuring, or filtering information and can run independent of the main query. In contrast, a correlated subquery cannot be executed on its own because it's dependent on the values in the main query. Additionally, a simple subquery is evaluated once in the entire statement. A correlated subquery is evaluated in loops, once for each row generated by the dataset. This means that adding correlated subqueries will slow down your query performance, since your query is recalculating information over and over. Be careful not to include too many correlated subqueries, or your query may take a long time to run. Here's another, smaller example of a query in which you can use a correlated subquery. let's answer the question, what is the average number of goals scored in each country across all match seasons? This is an easy enough question, right? You simply join the match table to the country table on the country's ID and extract the country's name, take an average of the goals scored, and group the entire query by the country's name, yielding one row with an average value per country. A correlated subquery can be used here in lieu of a join. Take a look at the outer query first. The name of the country is selected from the country table, aliased as C. The second column selected is a scalar subquery, selecting the average total goals scored across seasons from the match table. You'll notice that the where clause asks SQL to return values where the inner match table's country ID column matches the c.id column in the outer query's country table. This way, the entire join is replaced and the results are identical. Building on the previous lesson, another important type of subquery to learn is the nested subquery. Nested subqueries are exactly as they sound. Subqueries nested inside other subqueries. As you saw in the previous chapter, information in a database is often not in the format you need to answer a question. Some types of questions you answer may require multiple layers of transformation and filtering of data before you extract it into the main query. Let's start with an example. The query you see here is similar to the previous lesson, where we selected the average number of goals scored in a match within each country and compared it to the overall average using a subquery in select. This third column calculates the difference between each country and the overall average. The resulting table looks like this, with one row for each country and one column for each of the two calculations. Let's answer a similar question with an additional layer. How does each month's total goals differ from the monthly average of goals scored? The query here, similar to the previous one, answers this question. Let's take some time to walk through the necessary steps to get this result. The subquery logic reads like this. First, select the sum of goals scored in each month. The month is queried using the extract function from the date. Here are the results of that first inner subquery, which includes results for months 1 through 12. Next, you can place the subquery into the second outer subquery to calculate an average of the values generated in the previous table, giving you the average monthly goals scored. Since this result is a scalar subquery, you can now place it in the main query for calculating the final dataset. Finally, you can place the entire nested subquery in the select statement, giving you a scalar value to compare to the sum of goals scored in each month. Here are the first 4 rows of the final query, which generates a sum of goals scored in the month and a column subtracting the goals scored from the overall monthly average. It's important to note that nested subqueries can be correlated or uncorrelated. They can also be a combination of the two. The inner subquery can be correlated, the outer uncorrelated, or vice versa. And each of the correlated subqueries can reference information from an outer subquery or the main query. It entirely depends on the problem you're looking to solve. Let's look at an example. This query answers the question, what is each country's average goals scored in a match in the 2011-2012 season? This is fairly similar to the previous chapter, except it takes one additional step. It has a second nested subquery inside the select statement, and the outer subquery has a statement correlating with the main query. The result you see here is a table with a column that identifies each country's average goals scored in the 2011-2012 season. As you probably noticed, the queries we have been setting up are quickly becoming long and complex. It can become difficult to clearly keep track of each piece of your query, why you need it, and whether or not it's necessary. In this lesson, we'll cover a common method for improving readability and accessibility of information in subqueries, the common table expression. Common table expressions, or CTEs, are a special type of subquery that are declared ahead of your main query, just like you see here. Instead of wrapping subqueries inside, say, the from statement, you name it using the with statement, and then reference it by name later on in the from statement as if it were any other table in your database. Let's rewrite a query from an exercise that you completed in Chapter 2 by using a CTE. The query you see here uses a subquery, S, in the from statement to generate a list of country IDs and match IDs that meet a certain criteria. Specifically, we only wanted matches with 10 or more goals scored in total. This subquery is then joined to the country table, and the number of matches in the subquery is counted in the main query. Here are the results of that query: a short list of countries with very few high-scoring matches. In order to rewrite this query using a common table expression to represent the subquery, simply take the subquery out of the from clause, place it at the beginning of your query, declare it using the syntax with, followed by a CTE name, and as. So here, we're starting our CTE S by stating with S as, and then placing the subquery inside parentheses. It's now a common table expression. Finally, complete the rest of the query the same way you would if the CTE were an existing table in the database. You select the country name from the country table, count the number of matches in the CTE S, join S to the country table, and then group the results by the country name's alias. The results, you guessed it, are identical to the previous query setup. If you have multiple subqueries that you want to return into a common table expression, you can simply list them one after another with a comma in between each CTE and no comma after the last one. You can then retrieve the information you need into the main query. Just make sure you properly join the second CTE as well. So why are we learning yet another method of producing the same results in a SQL query? Common table expressions have numerous benefits over a subquery written inside your main query. First, the CTE is run only once and then stored in memory, so it often leads to an improvement in the amount of time it takes to run your query. Second, CTEs are an excellent tool for organizing long and complex queries. You can declare as many CTEs as you need, one after another. You can also reference information in the CTE declared earlier. For example, if you have 3 CTEs in a query, your third can retrieve information from the first and the second CTE. Finally, a CTE can reference itself in a special kind of table called a recursive CTE. We'll briefly discuss some more advanced applications of CTEs in the next lesson. At this point in the course, you're probably wondering why we're covering so many different methods of performing similar tasks. That's a great question. The simplest answer is that yes, there's a lot of overlap between use cases for joins, subqueries, and common table expressions. Many questions that you can answer can use these techniques interchangeably without sacrificing query runtime or the accuracy of your output. But these techniques are not identical. Let's take a minute to compare the techniques we've been using in this and the previous chapter. Joins allow you to directly combine information from 2 or more tables, and on their own, are mostly limited to simple combinations and aggregations of tables already present in your database. A correlated subquery allows you to combine information between a subquery and a table or another subquery. These help you simplify your syntax and circumvent the limits of a join, namely that you can't join two separate columns in one table to a single column in another at a time. We saw this in the match table, where you can't retrieve the team name from the team table for both the home and away teams at the same time. A correlated subquery can solve that problem. However, it's important to remember that correlated subqueries take a long time to process and will slow down your query performance. Multiple and nested subqueries are useful when your data requires multi-step transformations before it's in the form you need for your final query. Breaking down the steps of your query process allows for better accuracy and reproducibility in your work. Finally, common table expressions allow you to organize your subqueries sequentially by declaring them at the beginning of your query. Since CTEs are processed one at a time before your main query, you can reference information from a CTE created earlier, thus serving as an alternative to nested subqueries. So which one do you use? Often, it really depends on the database you're using, the field that you're in, and the questions that you're asking. In general, I recommend that you practice each technique with your own databases to determine which one allows you to best use and reuse your queries and generate clear and accurate results. Before we move on, I'll share a few examples of questions that each of these approaches can be used for. As you've seen, joins are a universally important skill when working with a database that has more than one table. It's fair to say that joins are necessary to understand each of the following techniques. Correlated subqueries are great for matching data from different columns in one or more tables, such as determining who each employee's immediate supervisor is. Multiple and nested subqueries are great for answering questions such as, what is the average deal size closed by each sales representative in the last quarter, which would require multiple steps to transform and prepare before generating the final query. Finally, CTEs are excellent for comparing a large number of disparate pieces of information. For example, you may want to create a summary table examining the marketing, sales, growth, and engineering team's performance on their key metrics last quarter. With CTEs, you can extract data about each team's performance, one after another, and combine them into a single query. You now have experience transforming data using simple subqueries, correlated subqueries, and common table expressions. Let's tackle another limitation you've likely encountered in SQL, the fact that you have to group results when using aggregate functions. If you try to retrieve additional information without grouping by every single non-aggregate value, your query will return an error. Thus, you can't compare aggregate values to non-aggregate data. You can work around this limitation using a window function. Window functions are a class of functions that perform calculations on a result set that has been already generated, also referred to as a window. You can use window functions to perform aggregate calculations without having to group your data, just as you did with a subquery in Select. You can also use them to calculate information such as running totals, rankings, and moving averages. So what's a window function? How do you use it? Let's start with a query from Chapter 2, where we answered the question, how many goals were scored in each match in 2011, 2012, and how did that compare to the average? This query selects two columns from the match table and then used a subquery in Select to pass the overall average along the data set without aggregating the results. The same results can be generated using the clause common to all window functions, the over clause. Instead of writing a subquery, calculate the average of home goal and away goal, and follow it with the over clause. This clause tells SQL, pass this aggregate value over the existing result set. The results are identical to the previous statement that used a subquery and select with a simpler syntax and a faster processing time. Another simple type of column you can generate with a window function is a rank. A rank simply creates a column numbering your data set from highest to lowest or lowest to highest based on a column that you specify. Let's take the same query as the previous example without the window function and use it to answer the question, what is the rank of matches based on the number of goals scored? We can answer this using the rank window function. In order to set this up, let's add a new column in select as you see here. To create the rank, you start with the rank function using parentheses followed by the over clause. Inside the over clause, include the order by clause and the column or columns you want to use to generate the rank. By default, the rank function orders the results and ranking from smallest to largest values. In the case of our data set here, this isn't particularly informative. You can easily correct this by adding the descending function to reverse the order of the rank, just as you would if you were using order by at the end of your query. You'll notice that the rank function automatically ties identical values, such as the first two results, and then skips the next value in the rank. There are a few key considerations when using window functions. First, window functions are processed after the entire query except the final order by statement. Thus, the window function uses the result set to calculate information as opposed to using the database directly. Second, it's important to know that window functions are available in PostgreSQL, Oracle, MySQL, but not in SQLite. The real bread and butter of window functions that differentiates them from subqueries and select are in the functions you can add within the over clause. One important statement you can add to your over clause is partition by. A partition allows you to calculate separate values for different categories established in a partition. This is one way to calculate different aggregate values within one column of data and pass them down a data set instead of having to calculate them in different columns. The syntax for a partition is fairly simple. Just like before, use an aggregate function to compute a calculation such as the average of the home goal column. You then add the over clause afterward, and inside the parentheses, state partition by, followed by the column you want to partition the average by. This will then return the overall average for, or partition by, each season. Let's take a look at how this works in a query. This example query from the previous lesson answers the question, how many goals were scored in each match, and how did that compare to the overall average? This is accomplished using the over clause, and the query returns the date, goals scored, and overall average. Let's expand on the previous question and instead ask, how many goals were scored in each match, and how did that compare to the season's average? We can do this by adding a partition by clause to the over clause from the previous slide. Specifying partition by season returns each season's average on each row in accordance to the season that each record belongs to. As you can see, rows 1 and 2 are matches played in the 2011-2012 season, and the season average column contains the 2011-2012 season average. Rows 3 and 4 are part of the 2012-2013 season and return the 2012-2013 season average. You can also use partition to calculate values broken out by multiple columns. In the query you see here, the over clause contains two columns to partition the average goals scored, season and country. The results set returns the average goals scored broken out by season and country. In row 1, a match was played in Belgium in the 2011-2012 season and had 1 goal scored throughout the match. This is compared to the value 2.88, which is the average goals scored in Belgium in the 2011-2012 season. Partition by is a pretty straightforward addition to the over clause. You can partition calculations by one or more columns as necessary to answer a question you may have. Additionally, you can use a partition with any kind of window function, a calculation, rank, or others that we will discuss further in the following lesson. Window functions can also be used to calculate information that changes with each subsequent row in a dataset. These types of window functions are called sliding windows. Sliding windows are functions that perform calculations relative to the current row of a dataset. You can use sliding windows to calculate a wide variety of information that aggregates one row at a time down your dataset. Running totals, sums, counts, and averages in any order you need. A sliding window calculation can also be partitioned by one or more columns, just like a non-sliding window. A sliding window function contains specific functions within the over clause to specify the data you want to use in your calculations. The general syntax looks like this. You use the phrase rows between to indicate that you plan on slicing information in your window function for each row in the dataset. And then you specify the starting and finishing point of the calculation. For the start and finish in your rows between statement, you can specify a number of keywords as shown here. Preceding and following are used to specify the number of rows before or after the current row that you want to include in a calculation. Unbounded preceding and unbounded following tell SQL that you want to include every row since the beginning or the end of the data set in your calculations. Finally, current row tells SQL that you want to stop your calculation at the current row. For example, the sliding window in this query includes several key pieces of information in its calculation. It first states that the goal is to calculate the sum of goals scored when Manchester City played as the home team during the 2011-2012 season. It then tells you that you want to turn the calculation into a running total ordered by the date of the match from oldest to most recent and calculated from the beginning of the dataset to the current row. Your resulting dataset looks like this, with a column calculating the total number of goals scored across the season, with a final total listed in the last row. Using the preceding statement, you also have the ability to calculate sliding windows with a more limited frame. For example, the query you see here is similar to the previous one with a slightly modified sliding window. The phrase unbounded preceding is replaced here with the phrase one preceding, which calculates the sum of Manchester City's goal in the current and the previous match. As you see in the data set here, the two rows in red are used to calculate the sum on the second row, and the two rows in green are used to calculate the sum on the third row. Throughout the course, we've covered a wide variety of methods for transforming, manipulating, and calculating data to answer a wide variety of questions in SQL. Specifically, you learned how to use case statements for categorizing, aggregating, and calculating information, and how to use simple subqueries in select, from, and where clauses. You also learned how to use nested and correlated subqueries and common table expressions to extract, match, and organize large amounts of data in order to generate a final table. Finally, you learned how to use some of the many window functions available to you in SQL. Let's put several of these topics together to answer one question about your dataset. Who defeated Manchester United in the 2013-2014 season? In the following exercises, you will generate a dataset that tackles one of the issues we've explored during this course, namely that it's difficult to retrieve the names of teams who played in a given match. Since this isn't feasible with joins, we will accomplish it with common table expressions. We'll also be using case statements to categorize the outcomes of matches based on whether or not Manchester United won a particular match. Finally, we'll be ranking matches by the number of goals they lost a match using a window function. If Manchester United happens to be a team that you favor, or if there are any other European teams you consider a rival to your favorite team, I encourage you to explore the European soccer database for yourself and create similar or completely different queries to answer your questions.